Hello everyone, and thank you for joining this workshop. In this presentation, we want to talk about UVM-SystemC randomization and give you some updates regarding the newest developments in the UVM-SystemC standardization efforts. First of all, I want to thank Dragos, Martin, and Stephan for working on the slides and also for working together in the SystemC Verification Working Group. First, let's start with an overview about today's workshop. First, Stephan will give an introduction about current verification working group activities. Then I will give an introduction into the CRAVE library and randomization for UVM-SystemC. Afterwards, Dragos will introduce the FC4SC library and functional coverage for the UVM-SystemC standard. Finally, Stephan will give a summary and outlook about further activities. Now I want to hand over to Stephan, who will give the first part of the presentation and introduce the current activities of the Verification Working Group.
Thank you, Thilo, for the introduction. First of all, before we go deeper into this presentation's topic, let's align on what UVM is about. UVM stands for Universal Verification Methodology. This methodology defines how a test bench is partitioned into components and how those components are set up and simulated. The partitioning into components which have specific duties enables you to reuse them for other test benches as well. For example, think of standardized protocols used over various devices. As such, a UVM test bench provides excellent support for coverage-driven verification when using constrained random stimulus generation, especially because of the separation of stimulus generation, result checking, and coverage collection. So why do we need UVM in SystemC? There's a growing need for standardization in system-level verification methodology. System-level verification enables users to include, for example, embedded software. But this means an earlier start of verification can make a difference in system design by identifying its issues earlier too. As UVM provides means to exchange the DUT while keeping the test bench, it provides a shortening of the test bench setup time when changing the DUT abstraction level. By using this UVM-SystemC implementation, it provides additional benefit because methodologies such as hardware-in-the-loop and others, which provide a C interface, can be adapted to be driven from a UVM-SystemC test bench. What are the UVM-SystemC principles? It complies with UVM-System Verilog to the most extent possible. Exceptions are usually language-based, such as reserved keywords, and other than that, classes, methods, and similar have remained the same. It also complies with plain SystemC by reusing its communication mechanisms, such as module hierarchies and transaction-level modeling. This makes test bench debugging simple to any SystemC user. And additionally, it is compatible with most EDA vendor solutions and flows by limiting the use of add-on libraries to avoid dependencies. The evolution of the SystemC-centric V&V ecosystem is evolving over the past years. It contains now almost everything for a proper verification system by having means for constraint randomization, functional coverage, and assertions. UVM-SystemC's goal is to provide a unification layer to group and support those aspects via a consolidated and consistent methodology. This approach is supported by a standardized API and reference implementation maintained by Accelera and its members. In a broader view, UVM-SystemC will be an integral part of the Accelera multi-language verification endeavors. The multi-language verification methodology is aimed at creating a methodology which takes the best aspects of all verification approaches and unifies them under a common umbrella, backed by using already available EDA tools. This is not strictly limited to UVM, as for example MATLAB and Python is also considered for inclusion. Detailed information will be presented in its respective short workshop at this year's DVCon. As the work for UVM-SystemC standardization is ongoing, Here's an overview of how far we have already progressed. The first public beta release was released already in 2016 after presenting it 1 year earlier as a tutorial in DVCon Europe 2015. This release included already all the basic building blocks to get started with UVM-SystemC. After that, further beta versions were released, fixing bugs and adding more and more functionality. Our current effort is focused on finalizing register-related topics and to provide a seamless inclusion for constraint randomization using CRAVE and functional coverage using FC4SC. Both will remain as a separate library to cater a broad usage. Thanks for your interest, and back to Thilo.
Thanks, Stephan, for the update and introduction. Now I want to talk about the second part of this presentation, about the CRAVE library and randomization for UVM-SystemC. I also want to thank Daniel Grosse and Mohammed Hassan, who have been working a long time on CRAVE and on the donation of the library to Accelera. Let's start with an overview. So, why do we need randomization for UVM-SystemC? The UVM-SystemC library has no randomization features itself, as randomization is not part of the UVM standard. Randomization is part of the System Verilog standard and is heavily used within UVM, but it's not actually part also of the UVM System Verilog standard. SystemC itself currently has no support for randomization within its core language. This is why additional libraries are required. One such library is the CRAVE library, which has been developed at University of Bremen, DFKI, and now moved to the Johannes Kepler University in Linz in Austria. And this library has been now donated to Accelera to form the standard of a UVM-SystemC randomization extension library. And also last year, a randomization adaptation layer for UVM-SystemC was released. So let's take a look into the CRAVE library. CRAVE stands for Constraint Random Verification Environment and is a C++ library which can be used for randomization. Its syntax and semantics closely follow the System Verilog IEEE 1800 standard, so it will kind of feel familiar. It supports random objects, random variables, C++ data type randomization, SystemC data type randomization. It supports hard and soft constraints, and in the back end, it supports efficient constraint solvers, which can be used for randomization. And it's available for as under MIT license. Also, you can download the current version of CRAVE at SystemCVerification.org. But this library has been now donated to Accelera, and we are working on a standard based on this library. Let's take a look at the architecture of CRAVE. CRAVE works based on a C++ constraint specification. It translates this specification of constraints and random variables into an intermediate representation, and then it does several steps in the backend. So there is some analysis, some constraint partitioning to find out what are the constraints which belong together. Then it can work on different kinds of solvers. So it supports some SMT solvers, some BDD solvers, and it can also run solvers in parallel. And it supports some kind of post-constraint generation analysis. So it will show you which constraints cannot be fulfilled and give you some errors, how to improve your constraints. Let's take a look at an example of CRAVE. At the top, some System Verilog code is shown, and at the bottom, the corresponding CRAVE code is shown. So we want to randomize a random variable v and define some constraint c on it, which says v is smaller than 10. And similar to System Verilog, where we just write rand and define the constraint. In CRAVE, we do use a CRAVE variable, and we specify the template type to be of the variable, and then we can define the constraint. What is different is that for CRAVE, as we are in the C++ world and we are using a library, we have to derive our item or object for randomization from a base class, and in this case, it is CRAVE sequence item. And we also have to define a constructor for the class, as it will be placed in an object hierarchy, and so we are using a mechanism similar to SystemC's naming mechanism by defining a CRAVE object name. So let's take a look how CRAVE can be combined together with UVM-SystemC. Therefore, we worked on porting the famous UBus example from the System Verilog examples over to UVM for SystemC. So UVM for SystemC supports or ships in beta 3 a version of the UBus example, and what we have added also as a kind of beta or outlook version is randomization using CRAVE. So this example, as it ships with the UVM-SystemC, beta is kind of the standard example as you know it from System Verilog, but it's missing randomization and coverage. And what we worked on is adding a version which supports also randomization. So let's take a look at this version. So let's take a look at the SystemC version of the UBus example. On the left-hand side, the System Verilog code is shown, and on the right-hand side, the corresponding SystemC version using CRAVE is shown. So what is different compared to normal UVM-SystemC? So instead of deriving from a normal UVM sequence item, we are deriving from a UVM randomized sequence item, and the CRAVE as the random variables are now defined as CRAVE variables instead of just using SystemC code. And on the left-hand side, you see how it looks in System Verilog. Also, the constraint syntax is quite similar. So you can see we are supporting enums for randomization, and we are also supporting vectors for randomization. So it is possible to basically port over the System Verilog example in a good readable way also to SystemC and CRAVE for SystemC. In the same way as we are supporting randomization of transactions items, we are also supporting the randomization of sequences. So again, shown the System Verilog and SystemC version. And in the SystemC version, similar as it's done to the System Verilog example, we have defined our own base sequence. It's called UVM or UBus base sequence. And this base sequence, in our case for SystemC, derives from a UVM randomized sequence. And this UVM randomized sequence also allows randomization. So also on this sequence, randomize can be called, as it derives from a CRAVE object item and from a normal SystemC UVM sequence item. So it's possible also to define constraints and randomization for sequence items. And so the syntax is also for sequences very similar to the one of System Verilog. Now I want to talk about another feature where CRAVE can be used in combination with UVM-SystemC. In UVM-SystemC, the UVM runtime phases are mapped onto the SystemC construction phases. So especially the UVM build phase is mapped on the SystemC before end of elaboration phase. This allows it basically from a UVM test to modify the design under test, because in SystemC before end of elaboration still allows it to modify the DOT. And this can be used in a UVM test to basically randomize the DOT. And this can be then used to send cool effects. So I will show you a small example how this can be done. Here we have a schematic of an ADC described in SystemC AMS. What we want to do is we want to set randomly one bit of the ADC to 1, so to emulate a stuck at fault. Also, of course, it's possible to set several bits to 1. And this modification of the DOT is possible just from the UVM test. So we don't have to interfere during the construction of the SystemC DOT. We can just later in the test modify the DOT. And now I want to show how this is possible. On the right-hand side, we have defined the CRAVE sequence item, which can be used to define the stuck at 1 fault. Therefore, we use the CRAVE1 hot function to randomly generate an integer with 1 bit set to 1, and we restrict it to 12-bit values. On the left-hand side, the UVM build phase of an UVM-SystemC test environment is shown. In this UVM build phase, we first connect an insertion point for the stuck at error using a DOT connector object. This DOT connector basically gives us access to a SystemC signal within the SystemC design hierarchy by specifying its name. What we are then doing is we are randomly calculating using the right-hand side CRAVE constraint a random bit vector where 1 bit is set to 1. And using a lambda function, we are using an OR as a kind of error mask to OR the incoming or previous value of the signal with the modified value. And so we are emulating a stuck at 1 fault. And this can be done in the UVM build phase inside a UVM test. So each time we run this test, we can emulate a different stuck at 1 fault. On the bottom right, you can see the simulation results for this error or fault inserted into the system. At the bottom, the input of the ADC is shown and we are giving in a ramp. And at the top, you see the output of the ADC. And what you can see is that we have not the same input-output. So we have some little glitches inside. And this is caused by the 1 at fault. So in this case, bit 5 was randomly chosen of the 12-bit ADC to be all the time at 1. So this was just an example how you can use UVM-SystemC in conjunction with CRAVE also to modify the DOT. So what is the current status of the integration of CRAVE into an accelerator standard? So as a working group, we are currently working on writing the standard document, and we are basically adapting the CRAVE concepts and making sure that they align with the SystemC concepts. This means, for example, building object hierarchies. There we have already in SystemC the SC object concept, and in UVM we have UVM object, and we are trying to align CRAVE to it so that it feels kind of similar. And another thing is we have to define a container type. In CRAVE it's called CRAVE variable as template type, and we are looking at other types like SC and a value to support them also in randomization and to give the SystemC user a kind of familiar interface. And what we are also looking is, for example, at the portable stimulus working group, which also defines a kind of randomization API, at least for C++, not for SystemC. And we are kind of making sure that the portable stimulus standard in the SystemC randomization standard based on CRAVE will have at least a similar look and feel. The other thing is what we are working on as a working group is a proof of concept implementation, which is then actually built on the CRAVE library and was donated, as I mentioned before. So what we have done as part of the standardization, we have done license cleanup, and currently we are working or playing around with the library to check that the syntax that we are defining is also working correctly and can be implemented. And another topic we are working on is on an updated build system so that the library can be used as easily as you expected from SystemC and UVM-SystemC using a normal AutoTools-based installation flow so that it's easy to use and also integrate into EDA tools. So now I want to pass over to Dragos from AMIQ Consulting. Dragos will talk about FC4SC and how functional coverage can be integrated into UVM-SystemC.
For this topic, I will introduce the FC4SC library and its features. Then we will spend some time on different aspects involving the coverage model construction. After that, I will show you a way to inspect coverage data at runtime. And next, we'll take a look at how the output looks like and how to generate one. Finally, I will talk about the next steps and the current work in progress for this library. Before going into the features, I'll describe a bit of the context surrounding the functional coverage implementation within Accelera. We are currently working on putting together a C++ library for functional coverage. This library is based on the FC4SC from AMIQ, having new features and improvement contributions from NVIDIA. It will be a pure C++11 header-only library with no included third-party dependencies, which means that it will be possible to use it without SystemC. As for its functionality, FC4SC provides ways to construct a complete coverage model and collect coverage data, following the definition of functional coverage from the SystemVerilog standard. The coverage model supports hierarchical scoping and contains internal separation between the lifetime of the data and the lifetime of the model. In addition to this, the dynamic model creation is supported, meaning that the coverage model can be constructed at runtime. You are also able to interact with the coverage data directly by defining your own visitor class and traverse the coverage data during simulation. Lastly, all the stored information can be dumped in an UChisDB output file, which is interoperable with commercial tools. Since the coverage model is based on SystemVerilog, it's natural that it is defined using cover groups, cover points, crosses, and bins. Cover group types and instances are both supported within the library alongside with options, and they all work the same way as in SystemVerilog. Sample function and conditional expressions are used for collecting coverage data and to control whether sampling is done for a cover point. I will not go into details for all of these bullets as they are part of the FC4SC core library and were presented at DVCon U.S. 2019. So for today's topic, I will just focus on what's new. Regardless, I will show a brief cover group example to act as a refresher. So as you can see on the right side, you can follow up the definition of a cover group type named CVGX, which extends from FC4SC cover group class. Inside, it contains two cover points with two bins each and one cross between the cover points. Next, we see an instantiation of the cover group type we just defined, followed up by a sample call. Coverage models also contain a scoping mechanism. There are two different kinds of scopes. First one is the declaration scope or the type scope, which tells you where the cover group type was declared. And the other one is the instance scope, which tells you where a cover group instance was created. Both of them are very similar to SystemVerilog and have a parent-to-child representation inside. To create a scope, you have to first extend the FC4SC scope class and then declare the scope inside your class by using the declaration macro. Then you can use CG scoped constructor inside the cover groups instead of the cover group constructor macro we used before. On the right side, we can see that we create a coverage model class and then we declare the COV model scope and then we propagate it to the coverage example cover group. As a result, the declaration scope of the cover group type is COV model CVG_EX. Below it, we have another class in which we define a second scope, main, and then instantiate the cover group defined above. The instance scope of this cover group will be assigned later at constructor by the user. Each coverage model must be situated in a context. Having multiple contexts allows you to separate coverage models within the same simulation. This is useful if you want to generate different coverage databases. If you don't want to do this, there is no need to explicitly define a context, as the library will automatically create and use the default one. But as an example, on the right side we can see the same coverage model defined on the previous slide, which is being instantiated multiple times but in different contexts. And the contexts are creating using the create new context function and deleted before the end of simulation by calling the delete context function. If you don't know the exact structure of your coverage at compile time, you can also define your coverage model during runtime. This can be done by using the dynamic cover group factory class. You just need to instantiate a cover group factory object and then insert cover points or crosses into it. Below we can see an example showing exactly this. We have this dynamic cover group object in which we create a cover point by providing its name and the sample function and condition as lambdas, and we next insert two bins inside the cover point, since the cover point cannot be empty. We also need to instantiate a dynamic cover group, and we do that by passing our previously constructed factory object to an instance of the FC4SC dynamic cover group class. Lastly, we must bind variables to the lambdas used for the sample function and the sample condition. In the example below, we declare the variables v1 and v2. We define the dynamic cover group created with our factory, and then we bind the variables to it. From there on, the cover group instance will behave the same as if it was an instance of a statically defined cover group and as if we didn't use the factory. As you can see in the last line of code, we can call the sample function with no problem. As I mentioned before, there is a separation between the coverage data and the coverage model. For example, the bin model is implemented by the FC4SC bin class, whereas the bin data representation is implemented in the bin data model class. I'll not focus on the difference too much, but what is important to know is that the lifetime of the data is dependent on the context it is defined in. Visitors will traverse the coverage data and not the coverage model. This means that the results can be different if you visit the same coverage object, but the coverage object is instantiated in different contexts. So you can use the visitor class to traverse any coverage data from cover group down to individual bins. As I mentioned before, the coverage output is an UChesDB file. To generate the output, you can use the XML printer, which is a visitor that collects all the coverage data. When you call the coverage save function, an output XML file will be created with the name that you provide, and it will contain the coverage that is dumped. Additionally, you can also specify a context containing the coverage model that you want to dump. Note that dumping of the coverage is not restricted in any way, and it can be done at any point during runtime. On the right side, we can see two context definitions, on which we call the coverage save function to generate the two coverage databases. So, what are the next steps? We need to standardize the functional coverage API and create vector documentation. More cross functionality also needs to be implemented, as there is currently no way to filter cross bins. There is some work left for decoupling between coverage implementation and declaration. This will allow the user to split cover groups in CPP and HPP files. And finally, we are working to create an official release. And with this, the functional coverage topic is finished. Thank you for listening.
Thanks, Dragos. Now I want to hand over back to Stephan to give a final summary and an outlook what is upcoming for UVM-SystemC.
Summarizing the upcoming Beta 4 release is planned for Q1 this year. Currently, we are working on implementing register-related items which we would like to be included for public testing. The CRAVE integration layer for UVM-SystemC has been already released, and now standardization efforts are ongoing. This includes also the donation process of CRAVE to Accelera, which has taken a few hurdles already and is expected to be finalized until Q2. AMIQ's functional coverage implementation, FC4SC, is now already part of Accelera. The next step is to start working on standardization. As always, input and support from interested parties is welcome to help further advancing standardization. On the next slide, you will find some links to our resources. Thanks.